You tap a button on your phone, and somehow a car just appears in minutes. It really does feel like magic, doesn't it? Well, behind that one simple tap is this massive, incredibly complex system, all working in perfect sync. Today, we're going to pull back the curtain and show you the actual engineering blueprint that makes something like Uber even possible.
So how on earth do they do it? I mean, how does a single system handle millions of people, track all of their live locations constantly, and then match them up almost instantly, all while keeping your wait time down to just a few minutes? That is the core challenge, and that's exactly what we're going to break down.
All right, here's our game plan. First, we'll look at the actual problem Uber has to solve. Then, we'll build the system piece by piece, dive into the tech that makes it feel so live, see how it scales globally, understand the really tough choices the engineers have to make, and then we'll put it all together.
Okay, let's start with the absolute basics. Before you can design any system, you have to know exactly what it needs to do from the user's perspective. What are the must-haves for a ride-sharing app to even work in the first place?
These right here are the non-negotiables. You've got to be able to request a ride, obviously. The system then has to find drivers near you, match you with one, and then, and this is key, show you exactly where they are on a map in real time. And all the while, it's giving you status updates, and at the very end, it handles all the payments and ratings securely. Every single one of these things has to be fast and super reliable.
So now that we know what we need to build, let's figure out how. We're going to start with the simplest idea you could think of, see why it completely breaks down at scale, and then build up to the modern, sophisticated architecture that actually powers Uber today.
The most straightforward approach, right, is to just have every single rider and driver app talk to one giant central computer. It would handle everything: user profiles, locations, matching, payments, the whole shebang. And it sounds simple, but when you're operating at Uber scale, this idea just completely falls apart.
Think about it. A single server is a huge risk. If that one server goes down, the entire Uber network goes with it. It's also really hard to scale. What if you just need more power for the matching part, but the payment part is fine? Well, with one big server, you have to scale up everything at once. The solution? You break it apart into smaller, independent microservices.
The best way to think about this is like a highly specialized team. You have one service that only handles user info, another that only tracks drivers. You have a brain that just focuses on matching. But the real key here is the API gateway. It acts like a receptionist. It takes every single request that comes in from the app and directs it to the correct specialist service. This keeps everything organized and lets each part of the system grow independently.
Okay, so we've got our team of services, but how do we get them all to communicate in real time? That little car icon moving smoothly across your map isn't an accident. It's made possible by some really clever tech. The old way of getting updates online is something called polling. It's like your app is the kid in the back of a car, constantly asking the server, "Anything new yet? How about now? Anything new?" It's slow. It's inefficient. Uber uses something called WebSockets. This creates a dedicated, two-way open channel. The second a driver's location changes, the server pushes that update to your phone instantly. No asking required.
Right, so we can push updates in real time. But how does the matching service find, say, the 10 closest drivers to you out of thousands in just a fraction of a second? I mean, searching through every single driver in an entire city for every single ride request would be impossibly slow. The answer is a technique called geospatial indexing. Instead of thinking about millions of individual GPS coordinates, the system divides the entire world into a grid of small, easy-to-manage cells. This basically turns a really complex location problem into a much simpler grid search.
Now, this is what I think is so cool. It's Uber's choice of grid shape. While lots of systems use squares, Uber actually developed their own system called H3, which uses hexagons. So why would they do that? Well, it's actually brilliant. In a hexagonal grid, every single neighboring cell is the exact same distance away from the center cell. This simple geometric fact makes incredibly complex calculations, like finding the closest drivers or figuring out a search pricing zone, way simpler and faster.
So we have this great design that works in real time for one city. But how do you make this system reliable for millions of users across hundreds of cities, all at the exact same time? That is a whole new level of challenge.
Well, this requires a whole toolkit of strategies. A load balancer is like a traffic cop, making sure no single server gets totally overwhelmed with requests. Caching is about keeping frequently needed info, like where drivers are, in a super fast temporary memory for quick access. Geo-partitioning is just common sense. You keep the data for London on servers near London to keep things fast.
And finally, an event-driven design means services don't wait around for each other. Instead of making a direct phone call, they leave messages in a shared mailbox. This makes the whole system more resilient, because if one service is busy, the others can just keep on working.
Now here's a crucial part of system design that a lot of people don't think about. There is no perfect solution. It's always a game of trade-offs, of balancing these competing goals to get the best possible result.
This is a classic dilemma in computer science. For something like a payment, you need absolute consistency. The transaction has to be perfect, accurate, and final, everywhere, all at once. But for a driver's icon on a map, you'd rather have availability. It's much better for the system to always be online and show you a location that's maybe a split second out of date than for it to go offline just to guarantee perfect consistency.
And here's another one. Should the system match you with the very first good driver it finds? Or should it take a few extra seconds to analyze more options to find the absolute perfect one? The first choice gets you a car faster, which is great for you. But the second one might be more efficient for the whole network. Uber is constantly tuning this balance.
And surge pricing? It's a perfect example of this balancing act in action. It's not just a business decision, it's an automated real-time engineering solution. The system detects an imbalance between how many people want to ride and how many drivers are available in a specific area, and it uses price as a lever to encourage more drivers to head that way and rebalance the market.
Okay, we have covered a lot of ground. Let's zoom back out now and see how all of these different ingredients come together to create that seamless experience we all know.
So here's the bottom line. Uber's magic is really just a combination of these key ingredients. You've got a flexible microservices architecture, all managed by an API gateway. You've got real-time communication powered by WebSockets. You have lightning-fast location lookups using that really clever H3 hexagonal grid. And you have a resilient system built on message queues and smart engineering trade-offs.
This architecture is just incredibly powerful for coordinating millions of moving things in a city. Today, it connects riders and drivers. But it leaves us with a really fascinating question for the future. What new possibilities open up when this exact same system starts connecting passengers to cars that can drive themselves?